In this video, we'll look at the amplitude of the forced response situation, how we can interpret this result. So previously we did a nasty calculation just working out a whole bunch of details for what the amplitude of the forced response was. There's a ratio RC over F0, where R is the amplitude of the response, C is the spring constant in this problem, and F0 is the magnitude of the force that's applied. So how do we interpret this? Well, in this context, right, R is the amplitude of the forced response. And based on how springs work, F0 over C is how far the spring would be compressed or stretched if I apply a single constant force of magnitude F0. And amplitude, I just mean the length of it, so I'm sort of comparing these two things that are very similar. R is sort of how far up and down this will oscillate. F0 over C is how far you would get to push it if you just shoved it forward by a force of F0. What we're actually computing here is the ratio of these two forces. And the important thing to realize that we'll see from some examples below is that this ratio can be bigger than 1. So if RC over F0, which is the ratio of the two things, is bigger than 1, this means that the amplitude of the forced response when I apply an oscillating force is bigger than it would be if I were to apply a constant force. So in some sense, when this happens, the oscillating nature of the force is causing a larger response than I would get with just a constant force. So this fact is the idea of practical resonance. The idea that the frequency here matters, and if I pick a frequency where this ratio is bigger than 1, this means that the fact that I have an oscillating input force here is causing a larger response in the system that I have. So in some sense, it's resonating instead of giving me a bigger response that you expect to see. It's increasing the output. It's a resonant situation. So the graph up here illustrates this fact. On the y-axis, we have this ratio. And on the x-axis, we have the ratio of the two frequencies, omega over omega 0. Which is what we had in our formula, sort of the important component that shows up in this answer. Omega 0 is the natural frequency. Omega is the actual frequency we're forcing at. And what we see from this graph is here is 1. And as expected, with 0 frequency, everything goes to 1 here because that's what you would expect to see. If you have no frequency, you have a constant force. Now in this graph, we have that the blue line is at b equals 0.4. The green line is at b equals 0.8. And the red line is at b equals 1.6 for different damping coefficients. We are assuming here that A and C, or our mass and spring constant, are both 1. Make things work out, but the ratio works out the same way. What you can interpret here is that it is in fact possible for things to be bigger than 1, right? With this 0.4 damping coefficient, I have a peak here of up to above 2.5 with a ratio just less than 1. And what this means is that if I have this damping coefficient for the situation and I apply a frequency that is just less than natural frequency, what I'm going to see is a response that is about 2.5 times bigger than what I would normally expect to see if I just applied a constant force. If I increase the dampening, I get a lower peak here at like 1.3. And if I increase the dampening even further than that, to say 1.6, I don't get a peak at all. It just goes from 1 down towards 0 over here. Again, we expect the 1 over here because that is if there's no frequency. If we oscillate way too fast, the spring can't keep up, and so you get low amplitudes there as well. So the important thing out of it is to be able to interpret this idea of what it means to have practical resonance, how it can come about, and what sort of needs to happen for it to exist. What this really means is that sort of having a frequency of the force application has an effect on the overall amplitude of the force response. It's possible to get an amplitude that is bigger than what you would expect from a constant response under this effect. And the fact that lower dampening, lower resistance makes this more likely to happen. As we reduce this coefficient further and further closer to 0, we'll see higher and higher peaks in this graph. You can sort of interpolate from these three. If I were to go to 0.2 or 0.1, it'd get more and more steeper, and this peak would get closer and closer to 1. And we'll see why in the future as B goes to 0, we end up in the undamped case, and that leads to a more significant issue at the point where this equals 1. You can think of this via undetermined coefficients and what that would look like, or how you actually solve the problem out. And we'll see it when we talk about the sort of phenomenon that comes out of this, the pure or non-practical resonance. So with those in mind, those are the important points to take away from this calculation. There's a lot going on with that calculation, but the main point is this amplitude depends on frequency, and in the right circumstance, you can get amplitude response that are bigger than expected because of this practical resonance phenomenon.